It's the same.
All right, let me have everyone's attention. First, thank you all so much for being here at our first What I Did Last Summer event. This is an awesome opportunity for you guys to see current research that's happening on campus or occasionally across the country, and often local employment opportunities or local internship opportunities as well. We plan to have about 4 or 5 of these across the entire school year. So if you participated in a similar opportunity, be sure to reach out to me if you already haven't about speaking at this event. It's a great way to gain experience, as well as have something to add to your CV at the end of the year for all of the work you did outside of school. So without taking up any more of the time of our speakers, let me, well, actually, real quick, be sure to write down any questions you have for any individual speaker, because it's going to be formatted slightly different than our normal talks. Basically, they won't take questions after they finish. We'll hold all of the questions for at the very end and have all of the speakers come back up at the same time. So be sure to hold any questions till the end. And let me first introduce Matt Hurst. So Matt is a Scott Science Scholar who is a junior computer science major. And this past summer, he spent time at Schneider Electric doing a whole host of things he's going to tell us about. Some of the other things that Matt does to stay extremely active on campus is participate in the Tartan Band, where he is a section leader in the high brass section, as well as in the orchestra. Prior to this year, he's been in a ton of other things, such as the MC3D Printing Club, as well as the Computer Science Club, and various other on-campus activities. So he's someone who has stayed very involved during his time here. And now I'm going to turn it over to him.
Thank you. So like Brett said, I'm a third year here at Maryville College. I spent my summer at Schneider Electric as a firmware engineering intern. And now I've been moved to an associate firmware engineer, so they let me kind of stay around while I'm still at Maryville College. So that's a great opportunity that I'll talk about a little bit later. First, I'm going to give a little bit of preliminary information about Schneider Electric. They're based out of France, and they operate worldwide, obviously, since I'm in America. They have a lot of presence specifically in North America, including Mexico. They have a lot of operations in Mexico. Their specialty is electrical assemblies like circuit boards, relays, panel boards, etc. And they have a huge emphasis on sustainability and green initiatives, kind of indicative of the times. I know a lot of companies are kind of flowing towards that point of view. Our location doesn't necessarily do much of that. We're more of a manufacturing location with an emphasis on R&D. And that's the team I work on, is a small R&D people of 6 or 7, or a small R&D team of about 6 or 7 people. There's one other firmware engineer, so there's 2 including myself. So Schneider Electric is a leader in IoT solutions, and that's what I do, is I develop new IoT solution product ideas in accordance with our team and our manager. So a little bit about IoT, to give a little bit of background information on it. That's just an abbreviation for the Internet of Things, and that's basically just the way that devices talk to each other and communicate with one another. And it's just the relationships that those devices have with one another. So everybody's familiar with this in some sort of way. Your cell phone is an IoT device. Your smartwatch is an IoT device. Your router is an IoT device. And anything that uses that router to communicate with another device is an IoT device. So we handle a lot of stuff through IoT. So a lot of solutions that we develop relies on IoT and those sort of connections, specifically cellular connection. And I'll kind of touch on that a little bit in the future. So this pertains to me because almost every project that I worked on during my stint at Schneider Electric, and including now, is an IoT project. So I only have one project that is not an IoT solution. That means only one project that I work on did not have a form of wireless communication. So that kind of speaks to the importance of learning this stuff. And I had no idea that that's what I was getting into, because as a computer science major, I thought I would be coding, and I am, but that's half of the job. So it was a pleasant surprise once I got into it to learn a little bit more about circuitry and electrical engineering, which I'll get into in a little bit. So just an overview of my projects before I get into them. I had 3 major assignments while at Schneider. The first was a testing assembly for incoming PCA boards. The second was an analysis of the viability of a time-of-flight laser tank measurement system. And then the project I'm working on now is the development of a new class of low-power wireless monitor. So a little bit about these here is the incoming product boards as a PCA boards. This is a circuit board with components already soldered onto them. So these boards come as is, they're ready to go, ready to be put into a product. The problem was that these were mass produced and sometimes came with defects, and people would have to manually test these in the plant, which was kind of tedious and really sketchy. So they wanted to come up with a more automated form to just clip them to a tester and let the machine do it. So the second point there, the viability of a time-of-flight laser tank measurement system. If anyone's ever used a laser tape measure, that's a time-of-flight laser. It basically sends out a laser and then comes back and measures how long it took, and that'll tell you distance. We currently measure tank levels, like the one you see in the middle there. Anything that holds liquid, we use a radar system. So it's a radar module that hooks to a tape that's got a floater in the liquid, and it sends the radar and waits for it to come back. And it uses that to measure how far away the liquid is, and then you can calculate the level of the liquid in the tank. This is okay, but this shows issues when using it for food safety, because you don't want to have to get your float that floats in, like carbon dioxide example for sodas. You have to go through certain qualifications to make that food safe, and it's kind of a pain. So he wanted a contactless, he being our manager, he wanted a contactless form to measure this liquid, and he had recommended maybe a time-of-flight laser sensor to shoot a laser down and get reflected back up. And then I'll talk a little bit more about that in a second. And then this third one is really the most interesting in my opinion. It's a new class of low-power wireless monitor that I'm going to talk about later because it's kind of in-depth. But it relies on a lot of cellular communication like I spoke about just a second ago. So now I'm going to get a little bit more into the details of these products. So the first one, the PCA testing assembly. This was for a Viber switch product. So we get boards in from a factory that's got all the parts already put on. And most of the time when you order boards, you have to solder the parts on yourself, but that's really tedious, especially when you're using them to manufacture products like this. You need a lot of boards, and that would be a lot of time. So we just have a manufacturer make them, we outsource them, and then they come in. So therefore, these boards have to be manually tested on arrival to make sure there are no defects. And like I said, this is a really long process. So I developed firmware to go on a testing assembly to automatically test these boards instead of having someone do it. So this ran on a microchip PIC18F family processor. Was developed in MP Lab. Basically, all that means is, you think of a processor that's on your computer, and you shrink it down to about the size of maybe the pad of your finger or smaller. And this is a microprocessor. So these can go on circuit boards to handle certain simple operations. So it's not near as powerful as your computer, your laptop, but it can do pretty complex things like testing these boards. So that's where the code actually goes. I wrote the code to go onto this processor to test these boards. So next is about this time-of-flight sensor. I'm not going to spend too much time on this because I kind of talked about it already. But my boss had said, okay, there's two solutions to getting rid of this radar tank measurement. And that's with this time-of-flight laser or a mass or pressure sensor. So that's basically just a fancy scale you put under the tank. He tasked me with analyzing if a time-of-flight sensor would be appropriate. And I came to a pretty quick conclusion that it wouldn't be, because most of the time liquids won't reflect a laser directly back up, and you're going to get a really skewed measurement. And that can be offset, but that's really not ideal. It would be way more ideal, surprisingly enough, for a mass or pressure sensor. So that's actually the route that we're moving forwards with. The time-of-flight sensor would work if you put a float in the liquid and had it shoot down directly onto the float, but that's ridiculous because that's what we're trying to get away from in the first place, because we're trying not to have to food safety grade a float for liquid. So I determined that that was not a valid option. This was based on an STM32 time-of-flight laser module. And then my third big project that I'm still working on, named the Cafe Monitor. There's no firmware name yet, but my manager just came up with a kind of rudimentary, simple name called the Cafe class. This is based off of an unreleased development kit from a company called Nordic Semiconductor, and they're a pretty huge company in this sort of field. They were gracious enough to give us several samples of one of their new boards that they came out with to test around and play around with. And they claimed that it would have extremely low power consumption with a hot cellular connection. And basically that means that it's already connected to the network and it had that communication ongoing. So it's pretty rare to see an extremely low power consumption with a hot connection. I mean, they were claiming 2 to 18 microamps, which is pretty low. So my manager assigned me to develop a proof of concept to see if this would work as a low power monitor. So you would hook this to a gauge, for example, like you'd see kind of your speedometer on your car, but it would measure tank levels. And it would then report to this device and it would send it somewhere else for data logging or analysis, predictive maintenance, and all sorts of things. So I was able to prove this rather quickly. So my manager thought that that was promising, and we moved this into our main site to develop the actual product, hopefully by July of 2025. And I don't know how that's going to go, but that's the plan for right now. So all of our approval and paperwork has been filed or is in progress. And I worked very closely with representatives from Nordic Semiconductor, which is another really important skill I gained from this experience, is professional communication with people that I do not know. So the challenges of this last project here, it was just hard. I mean, coming from a computer science major, having to deal with a lot of like electrical ideas, like resistors and capacitors and all that, I didn't know what those were until now. So that was kind of a learning curve. For communication, we needed SIM cards, and that's easy enough for your phone, but for IoT devices, it gets a lot trickier. No, we had to jump through a lot of hoops. So right now we're dealing with Verizon Wireless and are currently navigating those hoops. So the proof of concept I've generally got finished. So we're now in the awkward stage of moving that towards an actual production environment, which is what we're doing now. So just to kind of wrap up, this was a really good opportunity for me. My manager was impressed with the progress we made in the time that I made it. And he allowed me to stay on board as a contracted worker while I go to school. And I'm really grateful for my employer because they provide great flexibility regarding my classes. I can do a lot of remote work. They've got a great support system. My whole team is very helpful, and you know, it was scary going into, but it's a lot better having that great support system that really kind of helps you through concepts that you're not familiar with. Like I was not familiar with most of the concepts that I had to deal with on a day-to-day basis. So it was great to have that. So I guess I'm not going to open to questions.
All right, awesome. And we'll have our group of 3 speakers go ahead and come up here for the next one. I just want to go ahead and point out that like what he said at the beginning was, I expected to do computer science coding the entire time. Understanding that like the job wasn't actually what his expectation was, but then he had the skill set, he had the educational background to meet all of the other demands of the job. So don't be afraid to put yourself out there for an opportunity that you don't think you have all of the prerequisite skills for. All right, and now we're going to do something that we've never done before, and that's have a group presentation here at the What I Did Last Summer event. So I'm going to be introducing 3 fantastic senior students here. I'll go in order alphabetically, just not to offend anybody. But we have Reese Bailey, a senior biochemistry major, who's also on the volleyball team, also has been doing research for like what, a year and a half here now. So a lot of research, a lot of time going into that. We also have Kaitlin Koster, who is a senior biology major and the president of Tri Beta, as well as the, well, aside from that, she's done a lot of research outside of the college as well. Was it Maine that you went up to?
New York.
New York. So she went to New York, worked with Moonai, had a lot of experience with a lot of different aquatic realms at this point. So she's finding out what she does and doesn't like in that area. And then we have Izzy Wright, who is a senior biochem major, as well as the student body president. She's been extremely heavily involved in SGA her entire time here, as well as actively involved in research, and also just finding ways to fit in with the Scott Science Scholars Program, and ultimately causing us to form the Scott Science Scholars Associate Program. So 3 awesome students that I just want to congratulate on all they've done, and we'll make sure we give them a big round of applause at the end. But what they're going to be talking about today is their Townsend Water Project, and they're going to do an introduction together, and then they're going to branch off and talk about all of their different pieces separately. Without taking up any more of their time, I'm going to turn it over to them.
All right, welcome everyone. Again, my name is Kaitlin, this is Reese, and this is Izzy. And our project and what we worked on this past summer was the Townsend Little River Water Project. So to start, to give you a little background, this is a collaboration between the City of Townsend, Arconic Foundation, the Little River Watershed Association, and Maryville College. We have 10 sample sites along the Little River, starting at the entrance to the Great Smoky Mountain National Park and ending down at Wesley Woods. We also have 3 controls in Mountain Homes. Mountain Homes is an LLC that we've partnered with in the past that allows us to kind of sample on their property as kind of a pseudo of the Great Smoky Mountain National Park. This is a long-term, multi-year project that was started last summer by Izzy, which she'll talk about in a few minutes. And here on the screen, you can see a map of all of our sites. Those red dots are our sampling locations.
So our objectives in 2023 were to kind of create a baseline of our data for the health of the Little River and determine the quality of the water as it leaves the Great Smoky Mountains National Park and as it flows through the city of Townsend, and also to observe the amount of fecal coliform and E. coli and analyze its effects on the stream chemistry. Moving into this year, we expanded this baseline to a year-round monthly analysis. We increased the frequency and the quality of the E. coli and fecal coliform amount analysis. And we also started sampling macroinvertebrates, shout out Kaitlin, and then we also worked on developing a methodology for organic samplers to determine the presence of pesticides in the river. So here's Izzy.
Hello. So my little section of this project is I looked at the chemical profile, the E. coli, total suspended solids, and microplastic analysis. So with the chemical profile, every week that we went out, this started last year. Every week that we went out, we would use a lab quest, which you can see in the photo, paired with vernier probes that measured pH, dissolved oxygen, and temperature. We would also collect water samples to determine the amount of ion concentrations, so anions and cations like lithium, like nitrites, nitrates, and calcium by ion chromatography. And so some of the results from that are probe measurements are within expected ranges. So the water temperature is going to change with the atmospheric temperature, and pH and dissolved oxygen are going to go hand in hand. But with the ion concentrations, we also saw higher levels of calcium, and that can be attributed to the limestone rock, which the water runs over, that then reaches the calcium into the water. Moving on to the E. coli. So last year we did a monthly analysis of the E. coli, and using the old system, it wasn't really conducive and it didn't show consistent results. So what we did is we moved to in-house instrumentation. So we procured a TACTA and coal alert system to be able to analyze the E. coli more frequently and at a higher quality. So what we did is every week that we went out, we would collect a 1 liter Nalgene bottle of water from a good flow area of the river at each of our sites, and then put it on ice until we got back to the lab. So once we got back to the lab, we would put them in these prepared vials, which you can see Kaitlin holding, and they contain a powder that would fluoresce within the TACTA instrument. So the TACTA is more of an automated system to look at the E. coli and coliform levels, and it reads it itself, and then so you'll see the TACTA instrument in the bottom photo. And that sends a little email to my phone that tells me the amount of E. coli and coliform per sample. And then the coal alert, which you can see Reese doing in that picture, is we would take the water and then separate 100 milliliters from the 1 liter bottle and put in a prepackaged powder that would also have a color and fluoresce. So you can notice that Reese's little capture device is very yellow and also not the color of water. And that is because that is the dye. So all of those cells that look yellow are coliform presents. And then they also have a fluorescent dye in them so that whenever it's under a UV black light, it fluoresces. And if it fluoresces and is yellow, then that determines the coliform presence. And in order to look at our new instrumentation, we sampled 5 times in 1 month so that we can test the systems and see how similar they are to each other, as well as be in compliance with TDEC standards, which is the Tennessee Department of Environment and Conservation. So some of our results from this is that we saw the E. coli levels were definitely elevated in July, which is some of our most frequent visitor times in the city of Townsend. We also saw over time from March to the end of July into August, consistent high samples from site 4 through site 7. Most of these samples that we found are in compliance with TDEC standards, which is less than 126 coliform forming units per 100 milliliters. But we also saw a few in those sites from 4 to 7 that are elevated. And something that could cause the E. coli to happen is fecal matter. E. coli comes from fecal matter. And so upstream from site 4, in a river that empties into the Little River, we found a bunch of Black Angus cattle that had easy access to the water. And as you can guess, we're doing their business in the water. And so that's why you can see in this chart, over time from site 1 to site 10, you can see 4 through 7 had elevated levels from those fecal coliforms. For total suspended solids is basically just like the dirt and the junk that's just kind of like free flowing in the water. So what we would do is we would take a 1 liter Nalgene bottle in a good flow area, just like the E. coli levels, and then we would vacuum filtrate it onto these little like glass filters that really just look like paper filters. And so we would have to go through a 3-day drying and measuring process in order to standardize all of the filters. We would have to run distilled water through them and then dry them. So we would measure them and then filter the dirty water, and then after they were dried, measure them again so that we could tell the amount of dirt and organics that were free flowing. So the results from that is that each sample was below 20 milligrams per liter, which is the TDEC standard for very clean water. We did see some variation in this and after rain events, but that's also due to how rain and runoff can cause more sediment deposition in the water. For microplastics, when I attended the CERMAX poster presentations last year, I noticed at the graduate school fair that a lot of graduate schools were doing projects with microplastics. And so in order to be competitive in graduate school applications, I decided to apply microplastics to this study. And so the way that microplastics are evaluated is that you take a liter of water out of the river and then you filter it, just like TSS. So I decided, why not take the TSS samples that I've already used that would normally be thrown away and use them to look at the microplastics that are on it. And you can see a microplastic fiber on that sample, and that's through a microscope because they're itty bitty. So what I did is I took this filter and I rinsed it with zinc chloride to kind of separate the dirt and the plastics. Then I did a wet peroxide oxide digestion, and that basically digests all of the organics and all of the dirt, so I'm left with just plastic. And then so after that was finished boiling, I was left with this pulpy bit of filter paper and a bunch of plastics and water. So I centrifuged it and removed the supernatant off the top with a micropipette, and then filtered that onto a brand new filter. And then so my next steps are I'm trying to use IR spectroscopy to be able to compare them to a polymer library that I'm going to build with known plastics to be able to determine what type of plastic that I'm actually looking at. And so in future work, next year we would like to look at all your consistent E. coli testing to determine if the E. coli that we're seeing is from human or agricultural sources. I'm also going to continue using the TSS samples to look for microplastics, and I'm going to further develop the methodology and instrumentation for detecting those microplastic types in order to turn it into my senior thesis. And I'm not curious.
So this summer, I was looking at methodology development for detecting pesticides in the Little River. So pesticides have implications on the river health and contents. They can get into the river through agriculture, pharmaceuticals, sunscreen, all those sorts of things can end up in the river and affect the stream chemistry. So normally they're tested using biological indicators like mussels. So like just looking inside them to see whether the pesticides are present or not. So the pesticides that I look for are all herbicides. They were bifenthrin, carbaryl, lambda cyhalothrin, imidacloprid, olefin, and imidacloprid. So the way that I looked at this is, first, I kind of had to learn how to use the HPLC. I had never used that instrument before. It's a lot easier than you would think, but the picture at the top is a picture of the data you would kind of get from the HPLC. So the first thing I did was I created that, or I ran a test on a serial dilution of different parts per million of each of these pesticides, and then ran each of the pesticides individually to see where they would show up as peaks on this, to figure out later on what pesticides were present in the water. And the first test we ran was in spiked aquariums. So we got a huge drum of water from the Little River, and we filled 3 aquariums with Little River water and 2 of them with distilled water. We ran one high dosage of 300 microliters of each of the pesticides, a low dosage of 330 microliters of each of the pesticides, and then a control with just Little River water, one control of just the distilled water, and then a high dosage in the distilled water, which all of those will be tested on the HPLC. And then we put each of the passive organic samplers, there are 13 of them in total that went into the river. They went at each of our sample sites 1 through 10, and then each of our control sites. Each of them had 3 filter papers in them so that there are replicates of each one. And we measured the flow rate at each site so that we could figure out if that would have any problems later on, which I'll give you a hint, it caused some problems at some sites. And so we also, during the process, they all stayed out there for 3 weeks so that they could detect for a certain amount of time. And during that period of time, we used Izzy's TSS filters. And so they take out the dirt and stuff that's in the water, and mine looks at the pesticides that are in it. So we vacuum filtered through that to collect the stuff on my filters. We figured out my filters are very thick, and they do not like that to happen. So after the first 3 sites, we moved and we put it through Izzy's filter first, and then through my filter, and kept that to look at that on the HPLC as well to see if there is any pesticides present in there. And once we got our 9 that came out of the water out, we vacuum filtered, and then we rotovapped them to concentrate it down to just the stuff we wanted to look at on the HPLC, and they will be run on that momentarily. And so some of the takeaways that I kind of had from doing it, one of the issues we had is that, the Little River, when there's a rain event, it looks pretty fast, and little filters don't really stand a chance against that sometimes if they're exactly parallel with the water. So some of them started degrading after a couple weeks, and so we had to take some of them out early just because we feared losing the filters, and those are kind of important. They're kind of expensive, so we want to keep as many of those as possible. So in the future, we're going to create their grids on the 3D printed part of it so that the filter won't get bent inwards like it did this year. Another thing is that when there were those rain events, you literally could not see where the sampler was in the water, which was a big issue. So possibly using reflective tape or something like that on the bricks that we used to weigh them down in the water. Another thing is the signs we put up, like the sign up there, they are helpful and informative to the public. However, they might have looked like a scavenger hunt to those who took the information on that sign and were like, I don't know how I feel about that. So in the future, it might have to be consideration as to whether they're worth the cost that they play. Another thing is with the vacuum filtration, the C18 disc that we use to filter it through, it's thick, so it can cause a lot of time when you're vacuum filtering it. So making sure to have a good vacuum when filtering them is very important. And so finally, I'll hand it off to Kaitlin.
All right, my section of this project was using aquatic macroinvertebrates of the Little River as bioindicators. So you may be asking yourself, what are macroinvertebrates? So these guys are the larval forms of common insects that you may know of, such as caddisflies, mayflies, and dragonflies. To give you a visual example, That top guy up there is order Plecopteran. He will one day turn into a stonefly. That middle one is an order Coleopteran, will one day turn into a beetle. And the bottom one there is order Diptera, and he will one day turn into a cranefly. These guys are benthic organisms that are found in many bodies of water. They live in like the sediment of the riverbed, and they're part of the benthos, which is basically the assemblage of organisms that lives on that riverbed. And they're crucial to their ecosystem because they're nutrient recyclers and prey items for larger animals. In fact, if any of you are into fishing, you may recognize that top Plecopteran because a lot of bait is made to resemble macroinvertebrates because fish like to eat them. You may also be wondering, what is a bioindicator? So bioindicators are organisms whose presence or absence give us an indication about the health of the environment. Within these macroinvertebrates, some of the families are way more pollution tolerant than others, and in an index, they can be assigned a number that can be used for data analysis. For example, the bug I've got up there is commonly known as a helgramite. To me, that is a Megaloptera corydoidae. He gets a 5.28 on the index that I was using, which is pretty middle of the road. So that didn't tell us a whole lot, but we saw a lot of them out there. So to get into some of our methodology, we collected our samples via KickNet in early August. Early August was decided by our entomologist that we were working with from Jacksonville University, Dr. John Enns. He decided that that was the best time of year because of many years of research. So we just trusted that. We had 10 sites on the Little River, as we've said, and 3 controls in mountain homes, and we took 3 samples per site. So if you're quick at maths, you may realize that this is 39 samples, which is a lot of samples. We took primary, secondary, and tertiary samples and like differentiated between those while we were at the sites. And we selected riffles that had ideal depth and flow. A riffle is when the river gets shallower and starts going over some rocks and debris. So it's the not as still part of the river. And what I mean by preferred depth and flow, that top picture there shows Reese and Izzy with the KickNet. When we're collecting debris, ideally we don't want to lose any of that debris. So we don't want to choose a spot where the water would flow over the top of the net and we would have potential to lose debris. So really we were going for depth that was not taller than the net, but also not too shallow to where we wouldn't have a decent sampling location. And then as far as flow, we were just looking for some flow. We needed our debris to get into the net. So we were looking for, I believe, 0.5 to 1 inflow. When we were sampling, the KickNet is a meter by meter mesh net, about 500 microns. And it has 2 poles on the sides with these little stakes at the end. As you can see in that top picture, Reese and Izzy are holding those poles with the stakes in the ground. It's kind of at an angle that's kind of back so that the debris is able to be gathered in there. And then in front of the net, I determined a meter by meter square area where I would be doing my sampling. I removed any large rocks by wiping off both sides because a lot of these organisms are clingers. So I would wipe off both sides of the large rocks to make sure they got into the net. And then once all the large rocks were gone, I would step inside the square and do like a shuffle and kick thing in the square for about 90 seconds, just to kind of disturb that benthic zone and get all of the debris to go into the net. So once I was done collecting that debris, we would store it in jars with 70% ethanol for transport back to the lab for part 2 of the methodology. Once we were back in the lab, we would take a handful of the debris, put it in a porcelain tray, and sort it using forceps. So we would sort the debris from the organisms. And once we got about 160 to 240 organisms, I would then sort them to order. Oh, forgot to mention. So the reason we determined primary, secondary, and tertiary was because we did not pick all 39 samples. We only picked the primaries. The secondary and tertiary samples were kind of just for backup, just in case we needed to dip into them. And we did actually need to dip into them. So I'm just very thankful that we took them. So once they were sorted to order, I had about 5 to 7 orders that I would get per site. Just in case you're curious, those orders were Ephemeroptera, Plecoptera, Trichoptera, Coleoptera, Diptera, Megaloptera, and Odonata. And then I would move to my microscope where I would sort them to family. The reason you can't really sort them to family with the naked eye is because a lot of the differentiating features are very fine features. So you have to be able to zoom in to see them and to differentiate between different families. Once I had those numbers, I was able to take that along with the family that I determined that they were and calculate an average pollution tolerance value based on an index. I'll show an example of that here in a minute. But my results are that I'm still not fully finished. I'm actively working on all of these samples, and if you know me, you know that I'm constantly in the lab sorting bugs. But when I am done with that, I will run some statistical analyses to compare these sites to each other and to the controls to see what we could gather from this data. Here's an index calculation example. As you can see on the far left, those are all the orders I got in SS01. I only have 5 in this instance. And then the second column, you can see all the families. And then the third column, you can see the numbers that I pulled from the sample. And then on this far right column, you can see my TDEC index value. So the higher the number, the more pollution tolerant the organism is, and the lower the number, the less pollution tolerant. So as you can see, like 4 from the bottom, the Prolodidae, the Leuctrid, those 0 point ones, those are highly pollution intolerant. So the fact that they're able to survive in this river gives us some pretty good indication on the quality. But just those critters individually doesn't give us a full picture. So in order to come up with this calculated index value, I did some very complex math. Not actually. And I multiplied the number by the index value, added it all together, and divided it by that total number of organisms to get a 4.0 for this calculated index value. 4.0 is kind of middle of the road, leaning towards good quality, but I can't really make any, I can't draw any conclusions until I have all of the calculations and can compare them to each other. So that's an example of that. And then future work. Again, as we've mentioned, this is a very preliminary study. This is very baseline data, and we hope that future studies will include the entirety of the Little River. Also, as we mentioned, we started at the entrance to the Smoky Mountains and ended at Wesley Woods. That's not all of the Little River. The Little River expands, I think, 60 miles. So we'd love to do more of the Little River, and as well as more controls. We would have loved to have done 10 samples on the Little River to 10 controls. As you may remember, we only have 3 controls due to manpower and time. But again, this is a multi-year project, so there's definitely potential for more of that in the future. And a potential for plenty more of insightful data. So at this point, I will invite Dr. Duncan to stand up and do his plug.
Oh. So this is a really cool project, obviously, that Izzy's been working on for 2 years, and now Reese and Kaitlin worked on it this past summer and throughout this year. We anticipate that we'll have funding for this project for many years to come. And so we have 3 seniors about to graduate, which means we need people. So some of the stuff that's if any of this is of any interest to you, talk to them, get in touch with me. Some of this stuff you could start on right now if you want to do an environmental science internship this summer or this fall or spring. To start doing stuff, learning how to do E. coli, and then we can see where it goes from there.
Thank you.
Some of the opportunities that we have gotten to do because of this study is conferences. Last year, I was able to attend the Southeastern Regional Meeting of the American Chemical Society conference in Durham, North Carolina, which is where I presented last year's data in a poster format. My abstract was also submitted to this fall's CERMAX conference, but due to it being the same weekend as homecoming, I was not able to attend. But it was accepted, and it has now been submitted to the overall ACS spring meeting, which is in San Diego, California, and hopefully that'll be accepted as well. Reese is also going to do STEM.
Yeah, so I also submitted an abstract from my part of the project to the STEM conference that's in Chicago, and my abstract was accepted. I'm also submitting mine to the San Diego conference, so hopefully that'll also work out.
This is great to be a part of a large-scale, long-term project. And as I mentioned earlier, during CERMAX last year, they had a graduate school fair where a bunch of the graduate schools were there with their chemistry departments to kind of reach out to some of the students and be like, hey, this is some of the projects that we're doing. And I noticed that with a lot of the environmental science and chemistry projects, they only really worked with solar energy and micro and nanoplastics. And so I decided that, like I said earlier, in order to be competitive in grad school applications, I would apply microplastics to this project, which is what I'm currently doing. And this summer, so the way that you apply to graduate schools is, at least the way in my field, is that you cold email professors. So I was literally like looking these people up on their websites and being like, what kind of research are they doing? Okay, I'm interested in this. And so I would be like, hello, such and such. My name is Izzy Wright, and this is my research and who I am and why you should care about me. And do you have any money for me and space in your lab? And a lot of the time, I think I emailed like 30 or 40 people, and most of the time they said no, because they did not have money, they did not have space, or a lot of them were retiring. A lot. But finally, Dr. Suzanne Brander from Oregon State University was like, hey, I am interested in your summer research. Would you like to have an interview? And she offered me a spot in her lab for next fall, so fall of 2025. I will be moving up to Oregon, and I will be getting my PhD in fisheries and wildlife, focusing on microplastics in fish microbiomes and how those plastics pertain to endocrine signaling and endocrine disruption. So
Super cool.
Leading off of that, some of the things that we kind of learned from this summer is that we all actually really enjoy the work we did this summer. So it kind of led us all further in what we were doing. So Kaitlin still loves the field in the wildlife biology, and she's definitely going to pursue that, however she pursues that later on. And Izzy, obviously, graduate school, crazy awesome. That's really fun. And I learned that I actually really enjoy the environmental side. So that was really cool. Another thing is we did get to work in a team this summer, which is very similar to a lot of jobs and graduate school programs and different things. So it's really cool to be able to learn how to work with other people on research when you're not necessarily doing the same thing. Never in my life did I think I was going to learn how to order macroinvertebrates, but I did this summer. So that was a really cool experience. And it's actually something that I think I'll be able to look at for the rest of my life, especially like fishing, turning over rocks. That's pretty cool. And another thing is we all did very different things this summer. Like we did things all on the same project, but they were very different, which is really similar to how a lot of jobs work. So like pharmaceutical companies, they need business majors, and different STEM companies, or not STEM companies, different business companies need STEM majors. So you're gonna have to work with people from a lot of different backgrounds, and being able to work together and use each other's strengths and weaknesses to like work forward on a project is also a really like cool skill we kind of learned over the summer. And also we got to work really closely with some professors this summer who were kind of cool and awesome. And so that was really cool just because we got to learn more about different stuff on campus and off campus that we probably wouldn't have learned in another experience. So
Have to thank all of our people. This is a big project and required funding and help and a bunch of people. So the City of Townsend, Arconic, the Little River Watershed Association, they originally came up with this idea, and their constant like support and funding has super helped us this summer. Not to mention the Scott Science Scholars in the FIPSE grant, who allowed a few of us to actually stay here and do our research this summer. Dr. Duncan and Dr. Unger for being our fearless leaders and advisors this summer and throughout our whole experience here. Dr. Enns for being our wonderful entomologist from Jacksonville University. Dr. Conkle for her overall help and support, and especially with TSS, and Dr. Clark for being our coordinator and our spokesperson. So thank you to everyone, and thank you to all of you for being here. We really appreciate it. Now we're done.
So I know some of you may head out shortly, but before you do, I did want to say, if you did come in late and didn't sign in, make sure you sign out on the paper, or if Malachi wants to make sure that computer's loaded up, you can probably scan in with the scanner there. Other than that, we're going to open it up to questions for all of our speakers. They want to kind of make their way over here. Julie, you can flip on the lights if you would like. And what more do we want to know about all of these awesome projects, opportunities, things that were accomplished this past summer?
For the, I forgot exactly how you described it. Do you think that they were currently using to measure how much liquid is in a tank? How exactly did that work again?
So it was I don't know exactly how it works. It's very complicated, but it's a radar module. It's got tape coming out of the middle of it. And the radar basically is encapsulated in a little tube like that. It's very tiny. It shoots down and bounces off of a floater that would be floating in the liquid, and it goes back up the same tube in which it came. And it measures how long that took to come back. So to get there and come back. So if it's from the ceiling to the floor, it's going to take quite a while. But if it's right here, it's going to take about half the time to get there and come back. So you can use that to calculate the liquid measurement.
So Reese, given your experience, what do you think of methodology projects?
Well, so one thing that we learned from the samplers is that it collected it over a long period of time. So we don't actually know how much is in the river at a certain period of time, which is why we kind of pivoted to the filtration method where we did it one at a time. So we know the amount in like a liter of water on this day. So it's like, you know, the more specifics of it. So I think that it could be adjusted to make it better, but it's not there yet.
What other questions do we have? I know several of you interested in these fields. Andrew? Sorry.
This is for Matt, the chip that they created, or I guess they didn't create, but that you were developing. Is it something that they're like trying to give to the public as like an alternative for cellular protection?
The last project?
Yeah, last part.
No, so that would mainly be marketed towards businesses. Like if they have, for example, tanks that need, they do a lot of like liquid measurement. So if they have tanks that need measurements, basically that's targeted towards businesses to go onto that measurement device to communicate back to their headquarters or their office or their store to see like, okay, at 8 a.m. it was full, at 9 a.m. it was at 95, at 10 o'clock it was a quarter of the way full, so there's an issue, there's a leak. It shouldn't have been depleting that fast. So a lot of it's predictive maintenance for businesses. I think all of the company's products are open for sale for the general public, but I don't know that you would get too much use out of it.
Okay.
This is kind of a question for everybody, but if there are students in here who are interested in the work that you're doing or think they might be interested but really would like to see more about it, are there opportunities this semester that they could come and like water sample or watch what you're doing, Matt, or like any, you know, count bugs? Like, are there opportunities this semester for that?
Yeah, so as we said in our presentation, we're doing like a year-round look at the river. So we're sampling every month. So if anybody is interested, you could possibly go out with us on a sampling trip to sample E. coli, to sample ion concentrations, to sample pH, dissolved oxygen, temperature, that kind of stuff. And we can also show you how to quantify the E. coli in the lab.
As for me, our plant's got kind of strict security measures, so I don't know that people could really come in and monitor. But the good thing about microcontrollers and embedded programming is that anybody can really do it. You can kind of buy your own microcontroller. There's several retailers, and there's actually a lot of kits you can buy for people that know nothing about programming to start embedded programming. And it's really cool. It's really rewarding. So I would recommend people to do that. And then if they were really interested in maybe for computer science majors, like I said, I'm still with the company, so they could always reach out to me for future opportunities.
For the Townsend Water Project,
how much of your project actually is taking place outside in the field versus back in the lab, and like how do you find that experience, like the actual balance?
For me, we would sample about weekly, so we would spend about 6 hours out in the field on one separate day, and then most of the rest of the time could be spent in the lab. And a lot of this summer was all three of us, although we had separate projects, we were also continuously working on each other's projects. So we were helping Kaitlin sample the bugs, we were helping Reese rotovap, and I definitely messed up one of Reese's rotovap things. We're not gonna talk about that. But yeah. So I really loved being able to like kind of have a little bit of outside time, but also still being able to work in the lab.
Yeah, for me, definitely the same. We had about a week where we were out in the field every day, all day. And I haven't, like, that was our whole bug sampling time. So since then, I have been purely in the lab. I think we calculated that I'm going to spend probably over 80 hours on these bugs, and we only spent about 20 hours in the field on that bug week. So.
Yeah, it was kind of similar for me too. We kind of had like a push week where we kind of got everything into the water and where we got everything out. But I spent time on both their projects outside, so I got a bug for a whole week, which was really fun. I'm not being sarcastic. And so it was kind of, I want to say it was like 30 to 70. Outside, inside.
Do you have any final questions for our guest speakers? All right, well, let's give them one big round of applause.